Oral, followed by 6 spotlight presentations. The oral will be 12 minutes long, and you will have an opportunity to ask questions afterwards. Without further ado, I would like to introduce Esther Vertesh, who will be speaking about a neurally plausible model that learns successor representations in partially observable environments.
Thank you. Good morning, everyone. So this is joint work with Manoj Sahani from the Gatsby unit at UCL. One of the questions that we are interested in asking in this work is how do humans and other animals learn to transfer knowledge across tasks with different reward functions? For example, you might be interested in getting coffee at this conference, and you're able to quickly navigate to the nearest coffee station, even though that might be moved around during the week. Most of us are able to do this, even though we don't have an accurate GPS in our hands, using noisy sensory observations. That leads me to the second question: how do we retain this flexibility of transferring across different reward functions under state uncertainty in partially observable environments? Finally, how do brains might learn to solve these problems? I'll introduce you a possible solution that relies on successive representations that makes connections to a number of different experimental observations in neuroscience. So successive representations have been introduced as a representation for reinforcement learning that holds information not only about your current state, but also about future states visited under a given policy. It presents a hybrid between model-based and model-free approaches, leveraging fast value computation through cached values and retaining some of the flexibility of model-based approaches through an implicit model of the environment. Formally, it's defined as the expected discounted future occupancies under some policy pi, given a starting state S. If we have a reward function parameterized by a vector W, we can now factor the value function into two terms, the reward and the successor representation M. Now M holds information about the state distribution that is influenced by the environment and the policy. It is straightforward to generalize this representation to continuous domains by simply replacing the indicator function by a set of feature functions psi. For example, if you have features that look like this Gaussian bump here in this 2D environment, the corresponding successor feature M will take this elongated shape along the trajectory defined by the policy pi. Interestingly, these policy-dependent state representations have been observed in neural data as well. There's a number of connections that has been explored in rodent hippocampal and human behavioral data. So, as I've just told you, successor representations allow you to recompute the value function quickly under changing reward conditions, as I'm showing you now. And so far, we have considered a case when we have exact state information as available for learning. And as expected, the corresponding value functions and trajectories now directly lead you to the rewarded site. However, as I mentioned in the introduction, we are interested in a case when you don't have true state information available, but the agent gets access to noisy sensory observations. A naive approach to learning in this setting can lead to catastrophic failure modes in the value function and the resulting policy. And in this case, the trajectories from the right-hand side of the wall will keep hitting this internal wall. So next, I'm going to tell you how to formally handle state uncertainty, like arising in this example, and how to integrate that state uncertainty into learning successor representations. Decision-making under state uncertainty has been formalized under the framework of partially observable Markov decision processes. And in this setting, you have the reward that is directly dependent on some latent state S. The agent gets to observe noisy observations O through that state. And in this setting, the optimal strategy is to reconstruct a posterior belief about the state S given the observations, and then using that belief to adjust your policy to maximize reward in the environment. So now the question arises, how do we represent posterior beliefs? In discrete setting, the answer is quite simple. You can use a vector of probabilities, the probability of being in each state Si as a belief state. For continuous states, you now need to represent a density function P of S. A common approach here is to use a tractable parametric form like a Gaussian distribution. However, that can lead to severe approximation error in the cases of more complex beliefs like this bimodal distribution here. So we go with a different approach here, that is using belief states defined as an expectation of a vector of statistic function psi with respect to the represented distribution P of S. For example, if the statistic functions are Gaussian, the corresponding expectations hold information about the represented distribution implicitly. This code has been referred to as distributed distributional code, or DDC, and has tight connections to representing exponential family distributions by their mean parameters. This exponential family distribution with the statistic function psi, and the representational power of DDCs critically depend on the choice and the number of statistic functions, and the limit of infinitely many statistic functions. We arrive to kernel mean embeddings, actually. This representation has been proposed as a neural representation of uncertainty, how populations of neurons might go about representing distributions. We have recently shown that it's a viable representation for learning and inference in hierarchical latent variable models. And most recently, it has been used to explain effects of postdiction in perceptual inference. So now how do we put these two together? We have DDC belief states that represent uncertainty about your current state using expectations of statistic functions. On the other hand, we had successor features that by an analogous scheme, you can think about them as representing uncertainty about now future states using feature functions psi. In order to handle the partially observable case, for defining distributional successor features, we replace the state with belief states mu. And now notice that the statistic or feature function psi play a dual role here, both representing uncertainty about current and future states, and are also used to construct reward functions. So how do we learn distributional successive features based on this definition? We have to take care of two things. One is updating belief states mu, and the second is how, based on belief states, how do we learn and compute distributional successive features? We need to consider a PUMDP generative model where our observations arise from. And since we are interested in online learning, we're going to compute and update the belief states through Bayesian filtering. So now the DDC filtering posterior is conditioned on all observations up to time t, and it's updated through a function f that takes the previous belief mu and the new observation o. Both the recognition model f and the generative model are learned through a wake-sleep-like algorithm that we have introduced in earlier work. So now, for learning the distributional successive features, in the paper we propose 3 different methods that basically differ in terms of how much they need to rely on the learned generative model, and thereby spanning a spectrum between model-free and model-based approaches. In online learning, we use the DDC belief states directly to update the successor representations through temporal difference learning, while in offline learning, we use generated trajectories from the state space model and update the representations using those in a dyno-like fashion. In direct computation, we exploit the parametric structure of the generative model to compute successor representations through recurrent dynamics. So now, coming back to my previous example, we are still interested in a partially observed setting where we have the same noisy sensory observations, and to solve this RL problem, we now can see that using DDC belief states and the corresponding distributional successor features, we can correctly account for state uncertainty in this problem and can integrate that information into the learning of the value functions and successor features. So the resulting value functions reflect now correctly the geometry of the environment and leads to successful trajectories leading to the reward. To sum up the contributions from this work, we have generalized successor features to partially observable environments by exploiting the relationship between DDC belief states and successor features. We have proposed a number of different learning algorithms for learning successor representations that span a spectrum between model-based and model-free extremes, much like it has also been seen in human and animal behavior. There's a number of connections in neuroscience data that didn't have time to detail in this talk, but there's a few examples here. The connection between hippocampal activity of place cells has been previously pointed out between successive representations, and our model here makes a prediction of how these representations might change under state uncertainty. We propose a novel role for hippocampal replay in learning to infer spatial locations. And finally, this work unites two separate threads in the literature about the neuromodulator dopamine regarding sensory prediction errors and belief state representations. And with that, I would like to thank your attention, my collaborators, and financial support. Thank you.
Thank you very much. We have a few minutes for questions. To ask your question, please walk up to the microphone.
Hi, great work. Right over here. Yeah. Great work. Wondering whether it is relevant what is the horizon of the uncertainty, so the scale or the gamma parameter in the success representation, especially if you have a multi-scale one. You could have beliefs that in smaller scales there is uncertainty, or in larger scales. So in a volatile environment where things change, maybe that is more long-term or a longer scale, but in some problem solving, like taking an airplane from New York to come here, it's more at smaller scales that there is uncertainty. Is there any difference in the scale of uncertainty in your belief?
So not directly. The uncertainty first appears about your current state, and then how that's propagated into future states through the successive representation indeed depends on the discount factor that you introduced here. But since that's linear, it does not directly change the representation. You can choose, you still have to choose your discount factor, and you might be, as you were saying, might be better off choosing multiple discount factors.
If there's nobody else, I can ask another one.
Sure.
So the SR-DINA version that we had proposed had particular sort of memory bounds on how far into the past you would go to replay experiences. So for instance, there would be a recency sort of bias. There could be uncertainty bias for prioritized replay. Is there any kind of replay prioritization in the DINA version that you have?
Yeah, no, so we just considered naive replay where you randomly sample, but indeed you might want to prioritize replay through different mechanisms.
Thank you, great work.
We have time for one more question. There's no one else. I have a question. You mentioned there's quite some interesting evidence about connections to biological systems and to what degree these are, the proposed methods here are biologically plausible. I was curious about whether you could expand on that a little bit more, especially with respect to distributional successor features.
So I guess the points on biological plausibility are multiple. And one of them is that most of the learning algorithm that we have used here are all local. For example, even though you might want to take into account past information, past observations, you don't need to backpropagate through time, but through the beliefs. The belief represent a summary statistic that contains all information about the past, so you don't need backpropagation through time. And also for all the updates for the successor representation, you basically just need temporal difference learning, but now on a different feature representation, if you like, that has also been found mediated through the dopaminergic systems.
Fantastic. Thank you so much. Let's thank Esther again for a fantastic talk. Next up, we will have a block of 5 spotlight distributions. There will not be any time for asking questions between the spotlights, so please hold your questions for the poster session afterwards. Thank you.
Hey everyone, my name is Ophir, and I'll be talking about this dual dice work that I performed with my collaborators Inlam, Bo, and Li Hong at Google Research. So in this work, we're looking at reinforcement learning, obviously, and so we're all familiar with reinforcement learning. A policy starts at some initial state, produces an action, and then from the environment, it receives some reward and transitions to a new state, and so on and so forth. So in this dual dice work, we're looking at the following question, the policy evaluation question, asking, if I were to run this policy in my environment, what would be the average reward accumulated? So specifically, we're looking to estimate this quantity, right? This row of pi, which says, if I'm running my policy in my environment, what's the average reward, where I'm averaging over time using this gamma discounting. And the more interesting scenario is the off-policy setting, where you can't actually run your policy in your environment. The only access you have to your environment is through some off-policy fixed experience data set, usually from logging in the past of different behavioral policies. And in many cases, you don't even know what the behavioral policy was. And this is very relevant in health applications where the behavioral policy is really a human and you don't know what policy they were following. Okay, so how do we solve this problem? So the first thing we do is reduce the evaluation problem to a density ratio estimation problem. So we express the average reward of the policy in this form where we have the on-policy expectation of just immediate rewards. And then with this new expression for the value of the policy, we can rewrite the on-policy expectation instead as an expectation over our off-policy data set. And all that's introduced is this density ratio, right? And so now the key issue is how do you estimate this density ratio comparing the likelihood of your policy encountering some state inaction versus that state inaction appearing in your off-policy data set. And I want to emphasize that this problem itself is very hard because, well, first the numerator is the on-policy expectation, is the on-policy density, and you don't have on-policy access to your environment. And even the denominator, we have access to samples from the off-policy density, but we don't actually know the explicit density itself. So dual dice is looking at fixing this problem. How do we estimate these density ratios? So dual dice first defines this variant on the Bellman operator. It's essentially the standard Bellman operator, but with a zero reward. So the Bellman operator applied to some value function is just going to be gamma times the average next state action value function. And then the objective is given by this optimization. So we're going to learn this sort of state action value function, a sort of Q value function, to minimize this difference of two expectations. So let me focus your attention first on the first expectation. And what this first expectation is saying is simply learn your Q values to minimize squared Bellman error taking an expectation over your off-policy data set. So you can imagine you have these Q values or new values at each state in action, and this term is just saying, well, push those all close together. And if you only had this term, if you ignore the second term, the optimal would put just a zero Bellman error everywhere, right? But then we have this nice second term which says, at the same time as you're minimizing all the squared Bellman errors, also maximize the initial new values or Q values. And so these two terms trade off against each other, and what you'll end up getting is some non-zero amount of Bellman residual at each state in action, right? There'll be a little bit of slack introduced. And what's really magical and also useful for us is that this optimal slack, the Bellman residual of the optimal new state action value function, is exactly the density ratios we care about. And so that's dual dice, at least in its most basic form. It basically learns this state action value function to optimize this objective, and then the optimal solution of this objective gives you your desired density ratios. I encourage you to come to our poster to look at a couple extensions. So one is how to remove the explicit Bellman operator in both the objective and the solution, and two, how to generalize this from the squared Bellman error that you see here to almost any convex function of the Bellman residual. So hopefully I've piqued your interest, and I hope you can come to our poster number 205. Thanks.
Hi, I'm Matty, and I'm from the Whiteson Research Lab. And on behalf of my colleagues, I'm talking about Viral, a variational inference framework for reinforcement learning. Our work aims to cast the problem of finding an optimal policy in reinforcement learning to one of probabilistic inference. Indeed, there have been several attempts exploring this connection already, all motivated by the ability of applying approximate inference tools to reinforcement learning, extending our models in powerful and flexible ways. However, existing methods present a number of critical theoretical and practical problems that have not been addressed until now. We now review pseudo-likelihood methods, which attempt to reformulate the reinforcement learning objective as an equivalent problem of marginal likelihood maximization. These methods minimize the forward KL divergence between a target distribution that is proportional to the return and a variational distribution which contains the policy to be inferred. Contrast this to the classical reinforcement learning objective, which minimizes the reverse form of the KL divergence. Unfortunately, this formulation means that pseudo-likelihood objective methods reduce the influence of large negative rewards, which encourages the emergence of risk-seeking policies. More recently, the maximum entropy framework has become a popular alternative. All methods in this approach aim to maximize the maximum entropy reinforcement learning objective, which augments the reward in the classical objective with an entropy term scaled by a temperature parameter. While this avoids the problem associated with pseudo-likelihood objective, it introduces several theoretical issues. Firstly, deterministic policies cannot be learned from this framework. Secondly, in our paper, we construct a counterexample MDP to show that the optimal policy under the classic RL objective cannot be recovered by taking the mean or mode of the optimal maximum entropy policy. And finally, that the degree to which the two policies differ is highly sensitive on the temperature hyperparameter. In light of these shortcomings, we outline 6 desiderata that our framework satisfies. Firstly, our framework should be able to learn optimal deterministic policies. Secondly, the temperature should not be a hyperparameter. Thirdly, the framework should be able to deal explicitly with function approximators. Stochastic policies should be used for learning and exploration. Discounting can easily be incorporated into the framework. And finally, the objective should minimize the reverse form of KL divergence. We now present our variational inference framework for reinforcement learning, VIRAL, which satisfies all of these conditions. The principal object of interest in VIRAL is the Boltzmann policy, with a temperature that's equivalent to the mean squared Bellman error. Note that the Boltzmann policy is formulated in terms of any smooth function approximator. Under assumptions of exact representability, like in other RL algorithms, minimizing the Bellman error implies that the function approximator exactly represents the optimal action value function. Intuitively, in the limit of the temperature of the Bellman error tending towards 0, the policy tends towards a Dirac delta distribution, which is the corresponding optimal policy centered on the action that maximizes the action value function. One problem remains, however. Computing the normalization constant for the Boltzmann distribution is intractable for most MDPs. So instead, we resort to variational inference to approximate a variational policy, minimizing the reverse KL divergence between the Boltzmann and variational policy. We see that VIRAL offers an advantage over other entropy methods in that it adaptively balances exploration with exploitation. When the Bellman error is large, VIRAL's Boltzmann policy will be highly stochastic, as the model is not confident about the optimal Q function. This encourages the agent following the policy to explore globally to gather more data to better improve its estimate. Conversely, when the model is highly confident about the optimal Q function, the Boltzmann policy will center its mass on the modal action, corresponding to the maximum of the Q function approximator, encouraging exploitation over exploration. We then derive an actor-critic algorithm from our framework, maximizing the tractable evidence lower bound on our objective using expectation maximization. This yields an E step that is equivalent to an adaptive regularized policy improvement and an M step that is equivalent to policy evaluation. We also provide a probabilistic interpretation of our model and demonstrate that the empirically successful maximum a posteriori policy optimization algorithm can be derived exactly from our framework simply by changing our choice of prior without the need of simplifying approximations made in its original derivation. Finally, we test our EM algorithm on a number of Majoko continuous control domains against soft actor-critic, shown here in brown, and DDPG, shown here in light green. We test 2 variants of VIRAL, one with a fixed temperature in dark green, and another with an estimation of the MSBE in red. As you can see, the plots of our experiment demonstrate that VIRAL's algorithms outperform both of these methods in high-dimensional tasks, such as humanoid and ant. Thank you for listening. If you have any questions, we'd love to talk to you at our poster session after this spotlight.
Hi, I'm Alan, and I'll be talking to you about our work on unsupervised curricula for visual meta-reinforcement learning. So in RL, we've managed to build agents that specialize at certain tasks, but now there's a lot of interest in building more general agents that can solve more than one task. A common setting for multitask reinforcement learning is the contextual policy, where we condition the policy in some sort of given task description, like a goal. A more general setting is meta-reinforcement learning, where the policy actually also has to learn to infer the task from data. So for instance, we might have a recurrent policy that ingests state, action, reward tuples from the environment and has to learn to infer the task out of many tasks that it needs to solve. In environments with visual observations, this might also involve learning to search for and associate certain stimulus with reward. A central component of meta-reinforcement learning is the task distribution. So for instance, the task distribution might be a family of reward functions to be solved in an environment. And the task distribution really determines the nature of the task inference and execution strategies that will be learned by the agent. However, manually specifying task distributions can be tedious and challenging. So this begs the question of whether or not we can learn useful meta-reinforcement learning strategies by learning tasks that we form without supervision. So in this work, we consider a setting where we first train a meta-RL agent on an unsupervised task distribution, where this task distribution is derived from a density model of trajectories collected from the environment. After this unsupervised period, we can then transfer this agent to downstream test tasks. Prior work has considered a pipelined approach, where you first perform task acquisition and subsequently meta-learn these tasks. Here we argue that we would like to actually do both jointly. That is, the task distribution should adapt to the ability of the meta-learner in order to provide an automatic curriculum. What kind of tasks might we want? So on one hand, we want to prepare our agent to generalize and transfer to downstream tasks. And so we want it to see a diversity of tasks. But on the other hand, we want to actually facilitate task inference so that meta-learning is possible. So we want to kind of trade off between diversity in the task distribution and structure. A principled way to express this trade-off is through the use of mutual information. So for instance, we might consider the mutual information between trajectories that describe tasks and some latent variable z. So we can formulate this problem as an information maximization problem between the meta-learner's trajectory distribution and some latent task variable z. And we can optimize this objective using an expectation maximization style approach where we iterate between the E step, where we update the task distribution Q by incorporating new data from the policy, and the M step, where we actually update the policy, pi, on the new task distribution derived from Q. And in particular here, Q is a mixture model that is fit on top of a jointly learned discriminative representation, and that's what allows us to scale to pixel observations. So we consider two settings, one which is navigating a room filled with objects in VisDoom, and the other is pushing an object in a simulated environment with a Sawyer arm. First, we might ask what kind of tasks are discovered by our procedure. So we can do this by visualizing components of the task distribution, and we can project these components into the ground truth state space. So here I'm showing a top-down view on the left of the VisDoom environment, and this component corresponds to the agent first going straight and then turning to the right, like so. And here color is encoding the direction that the agent takes. So we can look at how the task distribution evolves, and we can see that as the algorithm proceeds, not only are new tasks accumulated into the distribution, but we also find that existing tasks are refined. There are several ways that we can consider transfer of the agent. One is, the most simple is maybe direct transfer, where we directly apply the meta-learner to test tasks. And we unsurprisingly find that we are not able to actually achieve perfect performance, and this is not surprising because at training time, we actually have no access to the test tasks. However, we can also try fine-tuning the policy that we've pre-trained, and we find that it is able to learn tasks more sample efficiently compared to baselines. And moreover, we can fine-tune the pre-trained policy on an entire task distribution, and in this case, we also find that it is able to learn these task distributions with less samples compared to baselines. So in general, we find that there are useful meta-RL strategies required in the sense that we see positive transfer. Thank you for your attention. Please come to our poster for more details.
Good morning. I'm Hao from the Chinese University of Hong Kong. It's my pleasure to introduce our work, the policy continuation with hindsight inverse dynamics to you. Solving the goal-oriented reverse sparse problem is an important but challenging task. In those tasks, the goal and the current state are combined as the input of the policy, and an trivial positive reward will only be assigned when the agent has achieved the goal. Here are some examples of those tasks. The first is the grid word navigation, where a goal and the starting state are generated randomly at the domain, and the objective is to reach the goal as soon as possible. The second example is the fetch-reach environment, where the agent is expected to manipulate a robotic arm to touch certain region in the space. Based on the observation that such goal-oriented tasks can be regarded as navigation in the state space with unknown geometry, we will use a 2D state map in the following of our presentation. Notice that purely random exploration will greatly limit the learning efficiency in such tasks. Our work mainly drew two inspirations from human learning. The first is that humans can learn from failures. The hindsight experience play was introduced to relabel the failed trajectories to assign hindsight credit as complementary of the primal sparse rewards. For instance, imagine that your agent is exploring the grid word navigation and is starting from the circle point and targeting at the red goal. And at this moment, your agent is quite poor, so it might only be able to reach the yellow state at the end of this episode. The HER points that if you regard the yellow state as the goal, at least your agent will learn how to reach such or similar regions. The second is human can extrapolate their knowledge or extrapolate their success. Imagine that you have learned how to reach a right-hand side of a starting point. I think it's not too hard for you to extrapolate your knowledge to reach a further position in that direction. Based on those inspirations of human learning, we propose our method of policy continuation with hindsight inverse dynamics to solve the goal-oriented reward sparse tasks. Let's first revisit the inverse dynamics, where inverse model is learned to predict the action AT between adjacent states ST and ST plus 1, and such transition pairs can be collected from any off-policy trajectories. And then we can train the inverse model with supervised learning. In order to use the inverse dynamics directly as a policy, we replace the latter state, the ST plus 1, with its goal correspondence, where we assume a mapping M between states and goals that encodes all of the information of the state to be regarded as a target. Notice that both this HID and the policy function take a state and a goal as inputs and then outputs an action. Actually, the HID itself is equivalent to a policy function. Intuitively, one-step HID will extrapolate well in simple linear cases or in flat spaces. But when it comes to complex geometry, we need to extend HID to multi-step settings so that our agent might have better extrapolation ability, but have better concept of its surroundings or the landscape. The challenge here is how to guarantee the multi-step optimality of the multi-step HID. And in our work, we propose the policy continuation method as a solution of this issue. The key idea here is testing the optimality recursively. If you are interested in the details, please come to our poster. And by regarding those tasks as navigation in the state space with unknown geometry, the policy continuation method, together with HID, actually solves such tasks by gradually learning the geometry using supervised learning. We demonstrate our method on the grid word navigation and the fetch-reach environment, and the experimental result shows our method improves learning efficiency, both when combined with traveling learning algorithms or work in isolation. Our supplementary material, demo video, and codes are released. You can scan the barcode for more information, and welcome to step by our poster at 194. Thank you very much.
There. Hello, I'm Rodrigo. I'm going to present this work. It's titled Learning Reward Machines for Partially Observable Reinforcement Learning. First of all, what is a reward machine? Reward machines are automata-based representation of the reward function. So the idea is that if you, instead of programming your reward function using Python code, you use this graphical representation, then we know how to exploit that representation to learn policies faster. Here are some results from a previous work where we show that our approach, DeepQRM, is outperforming hierarchical RL and double DQN. However, if you want to use this approach, someone has to program the reward machine and give it to the agent. In this work, we show how to learn reward machines from experience. We use reward machines as memory for partially observable RL. We extended QRM to work under partial observability. And we provide theoretical and empirical analysis of our approach. So to run this discussion, consider this domain. 3 rooms connected by a hallway. There is the agent. There is a button. When the agent presses the button, a cookie randomly appears in the red or in the blue room. And this problem is partially observable. So the agent can go and press the button, and now we know that there is a cookie, but we don't know where. So the agent checks the first room. It wasn't here, meaning that the cookie is on the other room. It can go there. It's the cookie, gets the reward, and then it can go and press the button again. Now, solving this problem requires memory, right? Because when the agent is in the hallway, it needs to remember whether it ate the cookie or pressed the button in order to know what's the optimal action. And this is not too surprising because this is a partially observable error problem, meaning that the optimal policy that considers the current observation is not equivalent to an optimal policy that considers the whole history, because the problem is no longer Markovian. So the most popular approach to tackle this issue is to train LSTM policies using a policy gradient method. Unfortunately, those approaches starve in the cookie domain. Here we see that while the optimal performance is way on the top, Acer, H3C, and PPO are way on the bottom. So what we studied here was to use reward machines as memory. This is how it works. Let's say that the agent can detect the color of the current room. When it presses the button, eats a cookie and sees a cookie. Then this reward machine becomes a perfect memory. And I will tell you how it works. So at the beginning of the episode, the machine is set to the initial state, U0, and the arrows are encoding these simple if conditions. If the agent presses the button, the machine will move automatically to state U1. Otherwise, it stays in U0. After every transition, we check this condition. In this case, the second condition holds, so the machine stays in U0. The agent presses the button. Now the first condition holds, moving the machine to state U1, where there is a different set of conditions. And then the agent will stay there until observing that the red room was empty. Now the machine moves to state U3. Until finally, when the agent eats the cookie, then the machine goes back to U0, and this starts all over again. Now, why is this a perfect memory? Well, because we can show that the optimal policy that considers the whole history is equivalent to an optimal policy that considers only the current observation in the environment and the current state in the reward machine. In other words, this reward machine is taking a complex non-Markovian problem and transforming it into a simple Markovian problem that we can solve using standard RL. Of course, the question then is, how can we learn these reward machines? So given a set of detectors and traces, learning a reward machine is actually a discrete optimization problem that we formalized in the paper, where the key idea was to learn a simple causal model that allows us to differentiate which reward machine is better than other. And to solve this problem, we use taboo search. This is the overall approach. We first collect some traces. We give these traces to our optimization model. The optimization model proposes a reward machine. And then an RL agent will learn a policy that considers the current observation and current state in the reward machine. And to do that, we try using double DQN and our previous approach that is called deep QRM. Some results, it basically works. In the cookie domain, these two approaches that learn the reward machine are finding near optimal policies, but there is not much difference between them. So then we try in a harder task, that is the two keys domain, where we see that our approach deep QRM is actually start paying off in comparison to just learning the policies in double DQN. If you want to know more about this research, come and talk to us in the poster session. Thank you.
This concludes our session. Please find the speakers and a lot of other amazing work at the next poster session. Thanks again to all the fantastic speakers.